Okay, hello everyone, welcome back again to my channel. Last time we have discussed about the quantum clock synchronization, which was my first lab rotation project at Okinawa Institute of Science and Technology, university where I am doing my PhD. This time I am making another. I'm going to talk about another topic, which is based on entanglement distribution between two distant parties. So, this time this is my second lab rotation. Uh, let's start the uh, let's discuss about this entanglement distribution protocols. And if you have any doubts, so you can email me. The email is in my description. Let's start. Okay, let me share the screen. Uh, share the screen. Okay. Uh, hmm. Yeah, I think my screen is visible. Okay. Okay. Let me start. Okay, so I'm doing my second lab rotation with Professor Bill Munro, and so today's topic is entanglement distribution protocols and its application in quantum key distribution. So let me start with the motivation. Um, the entanglement distribution between two distant parties plays a crucial role plays a crucial role in quantum networks, quantum key distribution, quantum teleportation, etc. So it is the quantum entanglement distribution is a fundamental building block of quantum technology. So, but there are several challenges that it face in both the theoretical research and experimental research, and the challenges are due to channel loss, detector inefficiency, limited success probability, etc. Here I have given some of the references with the limitation of these research papers. For example, the entanglement distribution have some protocols have very low entanglement generation rate, very less success probability, etc. So our goal is very simple. Like here, Alice and Bob are two distinct parties who wants to entangle their matter qubits, and they use photon as a mediator, and they will and we target a long distance quantum communication. Okay. So the content we are going to cover in this presentation is first we will go through the discrete variable protocol, then we'll move to continuous variable protocol, and then we'll consider channel loss, and we'll talk about different type of detectors that we have used here. Then we'll move to the applications, which is quantum key distribution. Then we'll conclude this presentation. So first, I'm going to talk about discrete variable based protocol. Then we'll talk about continuous variable based protocol. So the discrete variable based DV based protocol is widely well known, and it's experimentally realized in our in experiments. But the CV based protocol is nowadays it's an active area of research. So we are exploring the continuous variable, different type of continuous variable protocols here. So first let me start with the discrete variable, basics of discrete variable. So discrete variable is like the in discrete variable systems, the quantum information is encoded in discrete degrees of freedom, such as polarization, time bin, etc. Here we have considered single photon protocol, like single photons, which is finite dimension, which exists in a finite dimensional Hilbert space. So, so our target is first we will generate a atom-photon entangled state, which is given as psi here, and here consider a two-level atom, which has two internal states, are bright state and the dark state. So bright state can emit photon. So it corresponds with the single photon, and dark state cannot emit photon. So it corresponds with the vacuum state with probability, excitation probability P. So the preparation. So first we prepare a atom in ground state. Then we inject a weak excitation pulse. Then atom emits photon into the cavity. Then finally atom photon entangled state is generated. And we in the next slide we are going to see how this state can be used for entanglement distribution between two parties. So the protocol is very simple. Like Alice and Bob are two distant parties, and Alice and Bob will prepare their atom-photon entangled DV based atom-photon entangled state. The photonic qubit will propagate through the optical fiber to the central station, and the central station consists of beam splitter and detector. So the photonic qubits of Alice and Bob will interfere by the beam splitter, and after a successful detection, Alice and Bob's matter qubits are entangled. This protocol is widely well known and experimentally realized by people. So in the next slide we are going to talk about continuous CV, continuous variable based protocol. So first let me start with the basics of CV, continuous variable. So in continuous variable system, the quantum information is encoded in continuous variable, continuous degrees of freedom, such as optical field, quadrature, amplitude, and phase of the light, etc. And unlike DV systems, CV states exists in infinite dimensional Hilbert space. A popular type of an example of continuous variable state is coherent state, where mod alpha square is represents the mean photon number. The preparation, in preparation, first we'll prepare a atom in superposition state, as you can see in the animation. Then we inject a coherent state, that is alpha, into the cavity. Then this will work this will work like a CNOT type operation, which means that if the spin is up, then it does nothing, and if the spin is down, then the coherent amplitude will acquire a phase, which is alpha goes to minus alpha. And finally, the atom-photon entangled state is prepared. This is a type of cat type state. So in the next slide, we are going to see how this state can be used for entanglement distribution in our entanglement distribution protocol between two distant parties. So the protocol is similar as we have discussed in DV protocol. Here Alice and Bob prepare the CV based atom photon entangled state, and here we have used two type of atom field entangled state, which are CV1 and CV2, as you can see. Here the protocol is same. Alice and Bob will send the photonic qubit to the central station, and at the central station they interfere by the beam splitter, and after the successful detection, Alice and Bob's matter qubit are entangled. So here is the summary of our protocols that we have used in this project. So here the first protocol is DB based protocol, which is already explored by people, and the second one is CV1 protocol, and third one is CV2 protocol, which we are exploring here. So till now we have not considered any noise. When we talk about long distance quantum communication, so channel loss is a main source of noise. So we have modeled channel loss. So like mathematically, the channel loss can be modeled as Krauss operator, which is given here. So Alice and Bob's photonic qubit will experience this channel loss, and after this channel loss, they will interfere by the beam splitter, and the beam splitter operator is given here. Then after interfering with the beam splitter, after the interference, we detect the photons, which means here the detection means we are measuring the photons. So this mathematically it represented by the measurement operators, and depending upon the successful click pattern, we choose different type of measurement operators, so which we are going to talk in next slide. After that, mathematically we trace out the photonic part of the density matrix, and finally we get the density the density matrix of entangled density matrix of Alice and Bob. And here there are two figure of merits. The first one is success probability, which tells us like how often does the protocol works. And the second figure of merit is fidelity, which answers how good is the generated state. Okay, so the fidelity and success probability formula is given here. And next we are going to talk about different type of detectors that we have used here. As you can see here, we have used two different type of detectors. The first one is threshold detector. The idea is very simple. The threshold detectors says like if threshold detector says the presence, if the photon is present, then it says click. If the photon is not present, then it says no click. So if there are so many photons present, like suppose for example 5 photons are present, then also it says one click, which is a limitation. So we have used and another type of detector, which is called photon number resolving detector, which can count the number of photons, as you can see in the animation. So in the next slide, I am going to give a rough idea how these detectors works. So as we have talked about DB based protocol, the mathematical representation of Alice and Bob. The states are given here, and after the beam splitter, ideally the joint state of Alice and Bob is given here. And as you can see, so first we'll go with the threshold detector. So you remember I told that threshold detector says whether it's click or not click. Here for the threshold detector we take one click, which means that we are interested about these middle terms, which is up, down, and down, up, these bell type states. And here we'll post select this 0 1 and 1 0. So 0 1 means no click in the left side detector, and click in the right side detector, and 1 0 means click in the left side detector and no click in the right side detector. But the problem is we don't want this 2 0 and 0 2 term because it will reduce the fidelity, right? But by using threshold detector we cannot discard this event. So we need photon number resolving detector to discard this event, which will enhance the performance of the protocol. Next, I am going to talk about CV1 protocol, and the state representation of CV1 protocol is given here. And after beam splitter, ideally the joint state of Alice and Bob looks like this. And here, first we will consider the threshold detector, and the click pattern is both click. As the click pattern is both click, we can discard the first term and last term, and we'll consider only this middle term, and this middle two terms can be written as this, and which the left side term can be called like it's a even cat state, and the right side one is odd cat state. Even cat state means there are even number of photons, and the odd cat state means there are odd number of photons. So by using threshold detector we cannot distinguish these even and odd cat states. That's why we need photon number resolving detector to enhance the performance of the protocol. So the next one is the CV2 protocol, and the as we have discussed, the state presentation of CV2 protocol are given here, and after the beam splitter, ideally the joint state of Alice and Bob is given here, and first we'll consider the threshold detector, and here the click pattern is one click. So here as the state is symmetric, we can rewrite this middle state as this, and like we have seen in CV1 protocol, the threshold detector cannot distinguish between this even and odd cat states, so we need photon number resolving detector to enhance the performance of this protocol. So in the next slide, we are going to talk about the results. So to evaluate the performance of these protocols, we have plotted fidelity versus alpha and success probability versus alpha for different eta values. So in this case, we have considered threshold detector, and we are comparing CV1 and CV2 protocol. So here the dashed line represents CV1 protocol, and the solid line represents CV2 protocol, and we should compare the same colors with different protocols. Okay, so here as you can see from this left side of the slide, the CV1's fidelity is better than CV2, and from the right side of the slide for the plot, you can see the CV2 is better than CV1 in case of success probability. So there must be a trade-off between fidelity and success probability. So we have plotted the fidelity versus success probability in the next slide. So as you can see, we have plotted fidelity versus success probability in case for different eta values, and the dashed line represents CV1 protocol and the solid line represents CV2 protocol for threshold detectors. And you can it means like for a certain amount of success probability we'll get the fidelity. So here you can see clearly that this CV2 is the overall performance of CV2 protocol is better than the CV1. So we have compared CV2 protocol with discrete variable in the right side of the slide. Here the dashed line represents the DV based protocol, and the solid line represents the CV2 protocol. And as you can see, the performance or the overall performance of this DV based protocol is outperforms over CV2 protocol. Then we'll move to another type of detector that we have talked earlier, that is photon number resolving detector. So we have plotted fidelity versus success probability here for different eta values individually, like for DV, CV1 and CV2 protocols. Here the dashed line represents the photon number resolving detector, and the solid line represents threshold detector. And as you can see, in every cases like DV and CV1 and CV2, the overall performance of the photon number resolving detector is higher than the threshold detector. Then we have compared the CV1 and CV2 here in case of photon number resolving detector. So we have plotted fidelity versus success probability for different eta values, and here the dashed line represents the CV1 protocol and the solid line represents CV2 protocol. And you can see the overall performance of CV2 protocol in case of photon number resolving detector is better than CV1. So we have compared the CV2 protocol with the DV protocol, and here we have plotted fidelity versus success probability, and the dotted line represents the DV based protocol and the solid line represents CV2 protocol. And as you can see, no protocol is completely better than the other. For example, here we take eta equal to 0.5, which is given in the black color. As you can see, till the success probability is 0.35, the DV protocol is better than the CV2. And then after 0.35, the CV2 protocol is outperforms over DV protocol. So hence we need some application, and we have considered the application in quantum key distribution, and as we know, the key rate is a main figure of merit in quantum key distribution, which is dependent upon both the success probability and fidelity of the protocol. So here in this slide we are the secret key rate for quantum key distribution is defined as the number of secure secret bits Alice and Bob can generate per use of the communication channel in a quantum key distribution QKD scenario. Here we have considered two types of protocols, which are BB84 and device independent QKD. and the mathematical formula for to calculate the key rate for this QKD protocols are given here, which gives like the secret key fraction multiplied with the success probability, and the HQ is the Shannon entropy. So in the next slide, we are going to plot the key rate versus the distance, which gives the key, how the key generation is affected by the photon loss. So here we have plotted the key rate versus the distance, and the blue line represents the DV based protocol and the orange line represents the CV based protocol. And as you can see, there is a crossing point. Let me zoom it. Yeah, you can see that there is a crossing point at approximately 14 kilometer, and the CV2 is better till 14 kilometer. Then and after that, DV protocol is approximately 1.2 times better than the CV2 protocol for BB84 protocol. And next we have considered another type of QKD protocol, which is device independent QKD. And as you can see here, the right side of the slide, the orange the orange curve is always better, and the CV2 is always better than DV protocol, which is approximately 1.6 times better, 6 times better. So in the next slide, we are going to conclude this presentation. So entanglement distribution between two distant nodes plays a crucial role in quantum networks, quantum key distribution, quantum teleportation, etc. Then this both discrete variable and continuous variable provides a viable approach for remote entanglement generation, and the photon number resolving detector enhance the performance of protocols, enhance the performance of the protocols in comparison to the threshold detector. And at the end, we have seen in the application of QKD, so we have seen in case of BB84 protocol, CV2 is better till 14 kilometer. However, in case of device independent QKD, DV is always better than the DV. CV2 is always better than the DV based protocol. So our future work are like here we have considered only one noise, only the channel loss. However, we can consider a different type of noise such as decoherence or the detector inefficiency, and then we can see another we can see another application like in quantum teleportation, and finally we can see how we can use this entanglement distribution protocol for for distant parties to build a quantum repeater. And that's it. Thank you so much for listening my talk, and if you have any question, you can ask me in the through the mail. So till now, thank you so much. Bye bye. See you.